A flange can look simple until the joint has to carry bolt load, seal a fluid path, and stay stable as chemistry and temperature change. On a ceramic flange, every hole, edge, slot, and sealing surface becomes part of the load path. Zirconia is used when the interface needs more crack resistance than many conventional oxide ceramics can offer, while keeping the wear resistance and chemical stability expected from a dense technical ceramic. That combination is why a zirconia ceramic flange is engineered as an interface component, not just a white copy of a metal flange. Most industrial 3YT's PSB grades retain metastable tetragonal zirconia at room temperature. Near a growing crack, local stress can trigger a tetragonal to monoclinic transformation. The associated local volume change creates compressive shielding around the crack tip, which helps resist further propagation. This is the core reason zirconia can reach much higher fracture toughness than many traditional oxide ceramics. Typical engineering data for dense 3YT's PSB place flexural strength around the 1 gigapascal range and fracture toughness roughly in the mid to high single-digit megapascals square root meter range, depending on grade and test method. High hardness supports wear resistance at contact surfaces, while the higher toughness gives the part more tolerance against edge chipping during controlled assembly. That low thermal conductivity can make zirconia useful as a thermal break compared with many structural materials. Its thermal expansion is around 10 to 11 parts per million per Kelvin, so the mating materials and temperature range still have to be considered to control thermal mismatch. Flange geometry becomes part of material performance. Ceramic bodies tolerate compressive contact well, but a concentrated load at a bolt hole or sharp edge can create local tensile stress. Bolt circles, slot ends, chamfers, sealing landwidth, and face flatness therefore affect how stress moves through the part. A ceramic flange should never be dragged into alignment by the fasteners. The mating faces should meet without forcing, and bolt load should be applied gradually in a cross pattern so gasket compression develops as evenly as possible. When the process chemistry and temperature allow it, a compliant gasket can help distribute contact pressure and reduce local peaks. The tougher zirconia graded's margin, but good joint design is still what keeps a small defect from becoming a crack. Size selection begins with the interface that already exists. For a zirconia ceramic flange, outer diameter, bore, thickness, bolt circle diameter, hole size, slot geometry, sealing face, grooves, steps, and chamfers are normally drawing controlled rather than selected from a universal ceramic flange table. If the surrounding pipework follows a standard metallic flange pattern, the ceramic component can be designed to mate with that bolt layout and nominal size. But that does not automatically make the ceramic part a code-rated pressure flange. The complete joint still has to be engineered and qualified as an assembly. The elongated slots and mixed hole pattern visible here illustrate the point. Their purpose should be defined by the drawing and assembly function, not inferred from a generic standard. For non-standard designs, flatness, coaxiality, edge ready, and surface finish can be just as important as overall diameter. One representative application for a zirconia ceramic flange is a chemical process fluid interface around a pipe, pump, or valve assembly, where the process-facing joint must resist corrosion while keeping a stable sealing surface. At the sealing region, dense zirconia avoids the rust and corrosion scale associated with many metals, and it can be considered for a wide range of aggressive media after checking concentration, temperature, and exposure time. Its hard surface resists rubbing and particulate wear near the joint, helping the gasket contact area retain its geometry. The low thermal conductivity can also reduce heat flow through the interface when thermal separation is useful. The material does not remove the need for correct gasket selection, uniform fastener loading, or thermal expansion checks. In a real assembly, sealing reliability comes from the ceramic surface and the mechanical joint working within their limits. Ultimately, Zirconia does not need to replace the entire flange system. Its real advantage is placing a hard, tough, chemically stable interface exactly at the part of the joint that needs it most.